Here is me. Now imagine I was hungry and I wanted some chocolate. Now I could easily be greedy and I could eat all of that chocolate on my own. But let's say just for a moment that I was feeling particularly generous and I decided that I was going to share that chocolate with a friend. Now if we think about this in a real life kind of sense, we are going to have one bar of chocolate shared equally between the two of us. Now the amount of chocolate we're each going to get as a word is half a bar. And I can also write that in a more mathematical way, and it probably wouldn't be making too many assumptions to assume that we probably recognise this kind of way of writing a half. But let's really think about what that means, that mathematical way of writing this. We've seen this line between two numbers, one on the top, one on the bottom, before. We've seen this kind of presentation before when we talked about estimating. And we talked about how that line means something in particular. We talked about how that line is just a different way of writing a divide, where we have the number on the top divided by the number on the bottom. We have in this case 1 divided by 2. And what are we doing if we're splitting that chocolate in half? If we're sharing that chocolate between two people, we are taking one bar of chocolate and we are sharing it between two people. And that is exactly why a half is a half. We just then give it a name, the word half, because it's a particularly important, normal thing to do. Okay, so imagine now, half a bar of chocolate is quite a lot. Now I could easily eat half a bar of chocolate just as much as I could easily eat a whole bar. But for the sake of politeness, let's say, actually, I'm still feeling pretty generous. I'm going to share some out with another friend. So now, instead of sharing the chocolate between two people, we're going to be taking one bar of chocolate. We're going to be sharing it, dividing it between 3 people, and we are going to be getting a third of a bar. Again, third is just a word that we apply to this, where we are talking about the idea of one thing being shared among 3 people. Now, from this idea, we can pick out the first of our key facts here. When we are sharing the bar between 2 people, we will get more chocolate than when we are sharing the bar between 3 people. The bar is the same in both cases. Cutting it into 2 pieces is going to give us bigger pieces than cutting it into 3. We can say then that this idea of 1/2 and this idea of 1/3, we can make a comparison between them, and we can say that 1/2 is bigger than 1/3. Now we could say that as words, or we could say that using these, what we're going to call fraction forms, these numerical representations, which we're mainly going to use. 1/2 is bigger than 1/3. We are sharing this among more people, so there are more pieces, which means the pieces have to be smaller. Yes, the number on the bottom is bigger, but the overall fraction has to be smaller. So we can have our first key fact that 1/2 is bigger than 1/3. But a third is still a sizable amount of a chocolate bar. So we could add in another friend. We now have 4 friends, 4 people that we're sharing the chocolate bar between, myself and 3 other people. And again, from life, we are each going to get a quarter of the chocolate bar. A quarter of the chocolate bar, as in 1 bar, shared between 4 people. We are getting a quarter of the chocolate bar. Again, we apply this particular name. We've got the fraction form 1/4, where that line in the middle, that fraction line, is just a fancy way of writing a divide. We've got one thing divided by 4, because there are 4 people. We need equal shares, and we are calling those quarters because it's useful to apply names to particularly these ones. And again, while the number on the bottom is bigger, that just means we are sharing this out into more pieces. And if we have more pieces, the pieces themselves have to be smaller. So 1/4 is smaller than 1/3, which is smaller than 1/2. The bigger the number on the bottom, when we are dealing with these basic fractions, these 1/over things, the bigger the number on the bottom, the more pieces we're sharing it into. And in this case, in these particular examples, the fractions are getting smaller. Now we could continue this pattern. We could add an extra person in which case we'd be doing 1 shared between 5 and we'd be getting a fifth of the chocolate bar. We could add an extra person again, 1 shared between 6, and we'd be getting a sixth of the chocolate bar, one shared between 7, a seventh of the chocolate bar, and so on. And each time, the amount of chocolate that we are getting is getting smaller. More pieces, smaller pieces then, less chocolate in each share, and the fraction is getting smaller. Thing is though, I like chocolate, and the more chocolate we share out, the more people we share it out among, the less chocolate we are each getting. So maybe, to ensure that we're still getting a decent amount of chocolate, we need to add in another bar. So we now have 2 bars of chocolate, and we still have the 4 people that the chocolate is being shared out between. This time then, we have 2 bars being shared between 4 people. 2 bars divided among those 4 people equally. But what is the easiest way to share 2 bars of chocolate equally among 4 people? Well, surely the easiest way to share 2 bars of chocolate equally among 4 people would be to break this one into 2 and break this one into 2. As in, we would each get half a bar. 1, 2, 3, 4 halves of the bars, 4 people, half a bar each will give us the same as the 2 bars shared between 4 people. Now, if 2 bars shared between 4 people and half a bar are the same, it must be the case that those 2 fractions, while they look very different, are equal. Which is an idea we're going to come back to, but there's the same amount of chocolate when we have 2 bars shared between 4 people and 1 bar shared between 2, i.e. half a bar. So we are going to come back to this idea. We're just going to make a note of it up here first of all. That 2 shared between 4 and 1 shared between 2 are equal. And there's the first of our big ideas. Now that we have 2 bars though, we have more chocolate to play with. So maybe we're being greedy again. We're getting half a bar each when there's just 4 of us. Maybe we can get away with adding in an extra person. And we'd be getting 2 bars shared between 5 people. But again, there's still quite a lot of chocolate there. So maybe we could add in another person. Maybe we could add in a 6th person. And now that we've done that, we now have 2 bars that we are sharing out among 6 people. 2 bars divided into 6 equal pieces. But then what's the easiest way of sharing those 2 bars out among 6 people? Well, surely it's to cut this one into 3 and cut this one into 3 and give each person 1/3 of a bar. And once again, we've got this situation where 2 bars shared between 6 people and breaking 1 bar up into 3 is going to give us the same amount of chocolate. Splitting each of those into thirds and 2 bars shared between 6 give the same amount of chocolate, which means again they must be the same amounts. The fractions look different, but they must be the same amounts. They must be equal because we get the same amount of chocolate in both cases. And this can be a second key fact. And we are going to come back to this idea later as well. So we've got 2 things up there now. And we can come back to both of them shortly. And again, we can carry on with this idea. We could add a 7th person in. We'd have 2 bars shared between 7. We could add an 8th person in, 2 bars shared between 8, and so on. And each time, we're sharing those 2 bars among more and more people, so the amount we're getting is smaller. We're going to stick at the 2 shared between 6 for now, though. Because 2 shared between 6, we're getting 1/3 of a bar, which is still a sizable amount. But again, I like chocolate, and presumably all of my friends like chocolate as well. So maybe, just maybe, it so happens that I have another bar of chocolate. And we now have 3 bars of chocolate. Meaning that if we were sharing those 3 bars of chocolate out among the 6 of us, we would be getting 3 bars of chocolate shared equally between 6 of us. And what would be the easiest way to share 3 bars of chocolate among 6 of us? Well, surely the easiest way to share those 3 bars out equally among 6 of us would be to break this one in 2, and break this one in 2, and break this one in 2, and we would be getting half a bar each. And much like in these previous 2 examples, we have 3 bars of chocolate shared equally among 6, and 3/6 as a fraction, and we have 1/2 of a bar, 1/2 as a fraction, and they are giving us the same amount of chocolate, which means that those 2 fractions must also be the same. And this is going to be the third of our key ideas that we are going to come back to. That 3 over 6 and 1 over 2 are exactly the same. Same amount of chocolate in both cases. See, the thing is, now that we've got these 3 bars, we can maybe get away with having more people in. We could, for example, add a 7th person into the mix. And if we do that, we could take the 3 bars of chocolate and we could share it equally among 7 people. And we could keep going. We could do 3 shared between 8 and 3 shared between 9 and so on and so forth. We could keep adding extra bars of chocolate in, I guess, if we had more. But the problem is, at this point, it's getting quite confusing. It's very easy to look at, say, half a bar or a third of a bar and say, well, 1 bar shared between 2 and 1 bar shared between 3. You're obviously getting more chocolate if you're only sharing it between 2. So a half is bigger than a third. It's easy to look at those. But now that we're on 3 bars, it's difficult to tell whether we're actually better off. Yes, there's more chocolate here than when there were, say, 2 bars. But we're now sharing it among 7 people. We're sharing it among more people. So think back to a previous step. Well, at some point we were doing 2 bars shared between 5 people. But then in which case are we getting more chocolate? Are we getting more chocolate if we've got 3 bars shared between 7 people or 2 bars shared between 5? And it's very difficult to tell. We've got more chocolate here overall. We've got 3 bars compared to 2 bars. But we're also sharing these 3 bars between more people. We're sharing them between 7 as opposed to 5. So in which case are we getting more chocolate? Are we better off now with the 3 bars shared between 7? Or were we better off a while back with 2 bars shared between 5? And it's very difficult to compare. We don't have a decent point of comparison. So we can ask ourselves that question, which is bigger, 3/7 or 2/5? And we can make a note of that question. Which is bigger, 3/7 or 2/5? And what we're going to do is we're going to make a note of that question. We're going to keep that question in mind and we are going to come back to it. Because that question is one that we're going to work towards. We can take all of the things that we've just looked at, all of the tools that we've just had, we can turn them into something a little bit more proper, something a little bit more concrete, and then we can ultimately finish by answering that question and we can work out without doubt which is bigger, 3/7 or 2/5. Well, the first thing we need to do is we need to return to this idea of the fraction form and what it actually means. So we've already said, taking a particular example of 1/2, well, we've already said that this line in the middle is a divide, that this actually means 1 divided by 2, and that any fraction is top number divided by bottom number. It's always worth bearing in mind that fractions are a divide, and we will be coming back to this definition to do certain things with it eventually. But really this isn't the most useful way of thinking about a fraction. This is good as a start point. In particular, it's useful to bear in mind that fractions are to do with divides, not necessarily what the specific divide is. Because generally speaking, if we're talking about fractions, something like this, 1/2, we are meaning it to be read as a half, not as 1 divided by 2. Because reading it as 1 divided by 2 implies that we are going to want an equals sign. 1 divided by 2 equals a certain numerical value. And actually, leaving it in this form, this is a perfectly reasonable way of writing numbers. It is just a way of writing numbers that are less than 1, basically. In the case of most fractions, that are less than a whole thing that we've broken up. A slightly better and slightly more useful way of thinking about this is more of an out of kind of idea. 1/2. That yes, we've done a divide to take something, bar of chocolate, pile of money, whatever, and split it into, in this case, 2 pieces. Why 2? Because we're dealing with a half type of fraction, and a half type of fraction implies that we are splitting something into 2 pieces. A third type means we're splitting it into 3, a quarter type means we're splitting it into 4, a fifth into 5 pieces, and so on. So the number on the bottom is showing you how many pieces, equal sized pieces, you are splitting your thing into. The number on the top then, we are dealing with 1 out of those 2. We're splitting it into 2, and then we're only interested in 1 of those pieces. And that's a more useful idea. The number on the bottom of the fraction is how many pieces we're splitting something into, and the number on the top is how many of those pieces we are actually interested in. For example, if we had this particular shape and then we wanted to shade 3 out of 4 pieces of that shape, often we would read that as 3 quarters. We're dealing with a quarters type and we are looking at 3 of them. We first of all need to split this shape up into the right number of pieces. We're dealing with a quarters type, so we're going to split this shape up into 4 pieces. It doesn't matter how we do this as long as the pieces are roughly equal in size. That's 4 strips, so you could split it up into 1 horizontal line, 1 vertical line if you like. 4 equally sized pieces. How many of those pieces are we interested in? Well, we are interested in 3 of them. So there's 1, 2, 3, and the 4th one unshaded because we're only interested in 3 of those quarters. Notice that there is 1 out of 4 left unshaded. What happens if we take the 3 out of 4 and the 1 out of 4 together? There are 4 quarters in total. And 4 quarters is just a fancy way of saying everything. 4 out of 4, everything that's there. And that will be true for any kind of fraction. That 1 out of 1, 2 out of 2, 3 out of 3, 4 out of 4, and so on, 10 out of 10, 100 out of 100. Doesn't matter how big the pieces are. If we are looking at all of the pieces, we are looking at everything in total. It is just one whole in total. Notice also though that 1 divided by 1 and 2 divided by 2 and 3 divided by 3 and 4 divided by 4 and so on, treating those fractions as the divide that they actually are in secret, each of those sums will generate 1 as an answer. So either way we look at it, we are dealing with everything, the whole thing, the whole pile of money, the whole shape, the whole amount, the whole number of people, whatever. So we found when we were talking about chocolate that 1/2 and 2 quarters seem to be describing the same amount of information. Now we were talking about this in terms of the amount of chocolate that you'd get. 1 bar shared between 2 would give you the same amount of chocolate as 2 bars shared between 4. There's another way we could do this. We could prove this with that shapes idea that we've just thought about. Here we've got half a box shaded. I've shaded in 1 piece out of 2, so I've split this box into 2 pieces and shaded 1 of them. I could very easily make it so that this box was split into 4 equal pieces. There we go. And we now have 1, 2, 3, 4 equal pieces, i.e. we're dealing in quarters now, and 2 of those are shaded. The amount of the box that was shaded didn't change. All I did was drew an extra line on it, proving once again that 1/2 and 2 quarters seem to be describing the same information. But let's think about what's happened here. Well, as with lots of things, it can be helpful to see if we can spot any patterns. If there's any link between the 1/2 and the 2/4. And certainly it seems that on the top and the bottom of that fraction we have doubled the top and we have doubled the bottom, and we have ended up with a fraction that looks different but tells us the same stuff. And in fact we can extend this idea slightly to the other pairings that we found. We found also with the chocolate that 1/3 and 2/6 were the same. And again we have this timesing by 2 top and bottom with this pair. 1 times 2 is 2 and 3 times 2 is 6. Notice also that these would work the other way round. If we started with the 2/6 and moved down to the 1/3, we could be dividing by 2 top and bottom if we just switched this pair, or in fact this pair, over. We could be dividing by 2 instead. It depends which way around you're looking at the pair. And the final pair that we found that 1/2 and 3/6 were the same, or at least we're talking about the same amount of chocolate. And we seem to have this idea that on the bottom and on the top we have timesed by 3, top and bottom. Now hopefully this kind of idea should seem somewhat familiar. This idea of scaling up both parts of something, a mathematical form, to get something else that gives the same information but maybe looks slightly different. Hopefully this is reminding you a little bit of those equivalent ratios that we talked about in the ratios lesson. And in fact what these are 3 examples of what we call Equivalent fractions. Two fractions that look different but are still talking about the same proportion, the same information.
And in fact, this idea of equivalent fractions is so important to fractions overall. It's worth looking at this in one final way of proving that these equivalent fractions do exist. Consider these three circles. We could, for example, think about the fraction of the circles that are red. We've got three circles overall, and one of them is red, so therefore 1 out of 3, or 1/3, of the circles are red. Fair enough. Think about these circles now. There are 1, 2, 3, 4, 5, 6 circles overall, and 2 of them are red, so we have a fraction that are red of 2/6, 2 out of 6. But now consider the same 6 circles, rearranged so that they are spaced out differently. So there they are, the same 6 circles. We still have 2 red and 4 blue out of 6 circles in total. So that's still a fraction of 2 out of 6. But we can also say that 1/3 of the circles are red. Why can we say that? Well, because either, look at the top 3, 1 of them is red. Look at the bottom 3, 1 of them is red. So that's 1 out of 3 shown in 2 different ways. 1 out of the top 3 and 1 out of the bottom 3. Or we could think of these circles as not 6 circles, but 3 groups of 2 circles. 1, 2, 3 groups of 2 circles, where the first group is red. So therefore 1 out of the 3 groups. And we can do that perfectly fine because 1/3 and 2/6 are equivalent. They are describing the same relationship, but in different ways. 2 out of 6 is showing us 2 circles out of 6 circles, but 1 out of 3 could be showing us 1 group of 2 out of 3 groups of 2. And it's just a different way of grouping whatever it is you're looking at. We could do one more of these and prove this with one final example. We could think about these 9 circles where 3 of them are red, so we have 3 out of 9 red circles. 3/9 of the circles are red. But again, we could arrange these differently so that we were instead looking at them in this way. Now, if we look at the top row, we've got 1 out of the 3, the middle row 1 out of the 3, and the bottom row 1 out of the 3. So as well as having 3/9 of the circles being red, we also have 1/3 of the circles being red. Again, another way we could do this, we could look at 1, 2, 3 groups of circles, where each group of circles contains 3 individual circles. The first group is all red, the other 2 are not, so 1 out of the 3 groups is red. And again, it's just a different way of grouping them, that 1/3 and 3/9 are equivalent. They are not equal to each other in the sense that they are describing the same information, but they are equal to each other in that they are still describing the same relationship, the same stuff that's there, just in a different way.
So, classic question of this kind, fill in the missing number to make the fractions equivalent. So with equivalent fractions, much like equivalent ratios, we need to be scaling both top and bottom of the fraction in the same way. So we either need to times or divide top and bottom of the fraction by the same number. Whatever we do to the top, we're also going to do to the bottom, and we can times or divide. As long as we're doing the same thing to both parts of that fraction, we are fine. This first one, for example, 3/10 and something over 40. We start with the complete fraction, and we look for what we have done to, in this case, the bottom, to get from the 10 to the 40. Well, clearly we've times that by 4. To keep the fractions equivalent, we have to also do the same to the top. We have to times the top by 4. We're going to get 3 times 4 on the top to give us 12. And 3 out of 10 is equivalent to 12 out of 40. Second one then, 2 out of 8 and something out of 4. So we start with the complete one again. We're going to go from the 8 to the 4. And what have we done to 8 to get to 4? We have divided by 2. As again, we can divide when we are doing these as well. If we've divided by 2 on the bottom, we've got to make sure that we divide by 2 on the top. We're going to do 2 divided by 2, and we're going to get 1. And 2 out of 8 is equivalent to 1 out of 4. And the final one, something out of 15 and 1 out of 3. Well, we're going to start with the complete one again. We're going to start with the 1 out of 3. How have we gone from 3 to 15? we have timesed by 5, and if we've timesed by 5 on the bottom of that fraction, to keep the two fractions equivalent, we have to times by 5 on the top. So on the top, we're going to do 1 times 5, and that's going to give us 5. And 5 out of 15 and 1 out of 3 are equivalent. We can also use this idea of equivalent fractions to take fractions that look quite complicated, that have got quite large numbers in them, but are perfectly reasonable, and make them easier to understand. It's quite difficult to picture 240 300ths. There's nothing wrong with it as a fraction. We've got something, we've cut it into 300 equal sized pieces and looked at 240 of them. It's a perfectly reasonable fraction, it just doesn't make much sense. It's not something we can easily get our head around. But we could, in much the same way as we did with the ratios, if you think back, we could make this simpler. Use this equivalent fractions idea to break that fraction down into smaller and smaller numbers. As long as we are scaling top and bottom, either by timesing or dividing by the same number, we are writing equivalent fractions. So why don't we just look for something that the top and the bottom of this fraction will divide by? If it's something they'll both divide by, then we can make the numbers smaller. Now, when we're talking about dividing fractions, we're always talking about sticking with whole numbers. Fractions are complicated enough without bringing decimals into them. But we could notice that these two numbers, because they both end in 0, they will cleanly divide by 10. We could do 240 divided by 10 and get 24 on the top, and we could do 300 divided by 10 and get 30 on the bottom. And already 24 out of 30, an equivalent fraction there, is easier to work with. But maybe we could do this again. Maybe we could go a bit further. We might, for example, notice that these are both even numbers, and we could divide top and bottom by 2. And there's nothing wrong with us doing that. 24 divided by 2 is 12, and 15 when we do 30 divided by 2, so 12 out of 15. And again, the numbers are much easier to use. But maybe we could do it again. Is there anything that they will both divide by? A little bit harder to spot maybe, but we might, if we are thinking carefully enough, recognise that both 12 and 15 will divide by 3. And we would get 12 divided by 3 is 4 on the top, 15 divided by 3 is 5 on the bottom, and we would get 4 out of 5. Is there anything that they will both divide by? Well, actually, 5 is a prime number, so the only things it will divide by are 1 and 5. 4 won't divide by 5, and dividing by 1 top and bottom won't make any difference. So it turns out that that is as far as we can go. But clearly, 4 over 5 is a much smaller looking fraction. It still means the same, but it's easier to read. They are equivalent to each other. In fact, this process of cancelling down has a name, and what we've done in finding the 4 over 5 for this particular example is we have found the simplest form. Much like we talked about simplest form of a ratio, we've also got simplest form of a fraction. The only difference here is that the numbers are one above the other instead of being left and right of each other. But we can use this idea of equivalent fractions to cancel stuff down to find smaller numbers and find a simplest form. Now, we still don't really seem much closer to an answer to this question, which is bigger, 3/7 or 2/5. So let's think a little bit more about putting fractions in order of size.
So we have here a fractions chart with some common fractions on there. So we have 1 on the top row, then we have 2 halves, 3/3, 4 quarters, 5/5, 6 sixths. We've skipped sevenths because 7, not that common a fraction, but it would be next. Then we've got 8 eighths. We've skipped 9 as well because ninths don't tend to be that common a fraction, but they would come in that gap there. And then we've got 10 tenths. And again, this chart would carry on to 11ths, 12ths, 13ths, and so on. Each time, the fraction is getting smaller. So 1 is bigger than a half, which is bigger than a third, which is bigger than a quarter, which is bigger than a fifth, which is bigger than a sixth. So each time we're dividing by a bigger number on the bottom, the fractions are getting smaller. But we can do this comparison because we are only having fractions with 1 on the top. We are dealing with 1 half, 1/3, 1 quarter, and so on. Each time we are thinking back to that idea of taking one thing and splitting it into a certain number of pieces. Because these fractions all have a decent point of comparison, this 1 over something, we can make that point of comparison and work out which one is bigger, particularly if we have a drawing, but even if we didn't. One thing split into 3 is clearly going to be bigger than one thing split into 4. More pieces means smaller pieces if we're dealing with that one thing each time. Where this causes problems is if we're dealing with more than one piece, because we don't necessarily have that point of comparison. Like, for example, with our question 3/7 and 2/5. They're two different.
Now, even when we're dealing with fractions that seem a bit more complicated, if there is a common point of comparison, then it is easy enough to see which one is bigger. If we're looking at this question, for example, which is bigger, 4/9 or 5/9? Well, we're dealing with the same kind of fraction in both cases. 9ths in the first case, 9ths in the second case. There is our point of comparison. In this first one, for example, 4/9, we are dealing with 4 out of 9. So there is 1, 2, 3, 4. Out of 1, 2, 3, 4, 5, 6, 7, 8, 9. 4 out of 9. To have 5 out of 9, I'd have to shade an extra piece. I'd have to have an extra 5th piece here. So clearly, 5 out of 9 is bigger than 4 out of 9. 5/9 is bigger than 4/9, because we've got that common point of comparison. But what about when we haven't got that? What about when we haven't got a point of comparison between two fractions, when the two fractions are completely different? For example, just to pick a question at random, which is bigger, 3/7 or 2/5? We now have enough tools to deal with this question. So we've already seen that when we're comparing fractions, we need to have a point of comparison. The first kind of examples, the half and the third and the quarter and those sorts of ones, the point of comparison was that they were all single unit fractions. 1/2, 1/3, 1/4 and so on. The second example with the 4/9 and the 5/9, it was because we were dealing with the same type of fraction. But that's the key. We could do that because we were dealing with the same type of fraction, 4 out of 9 or 5 out of 9. These two fractions are not the same type. If they were the same type, then we could compare the fractions easily. But we're currently dealing with a 7th and some 5ths. Different types of fraction. But if we could rewrite them so that they were the same type of fraction, whatever that happened to be, then we could compare the size of the two of them. Do we have any way to change the type of fraction that something is? Well, yes, we do. Because equivalent fractions give the same information but written in a different way. So here's the really clever bit. Maybe we could use this idea of equivalent fractions to rewrite one or both of these fractions so that they are the same type. 3/7, 2/5. We are going to use this idea of equivalent fractions to rewrite them so that they are the same type of fraction. So we need to work out what type of fraction we're going to change them both into. We need a type of fraction that we can easily scale 7 and 5 into. So we need something from the 7 times table and the 5 times table. Because something in the 7 times table we can easily times 7 up to get, and something in the 5 times table we can easily times 5 up to get. So something in both will give us a point of comparison. Now anything that's in the 5 times table and the 7 times table will work. But the most obvious one is probably going to be the two numbers times together, because the two numbers times together, 5 7s or 7 5s, that's clearly in both times tables. And 5 7s or 7 5s, 35. Just to make the point, sometimes in other questions there might be a more obvious one, there might be a smaller number, there might be a bigger number. It doesn't really matter because you will always get a point of comparison if you use something from both times tables. So what we're going to do is we're going to, one at a time, scale these fractions up so that instead of being 7ths and 5ths, they are both out of 35. And we're going to do these one at a time. So I'm going to cover up the one that I'm not dealing with. I'm just dealing with the 3/7 first of all. and I'm going to times or divide. It's always usually going to be timesing with these kind of questions. I'm going to work out what I have times the bottom by to get to 35. In this case, it is clearly going to be times 5. Now, if I've times by 5 on the bottom to keep these two fractions equivalent, because that's the whole point of this, I'm going to have to times by 5 on the top. So on the top, I'm going to do 3, I'm going to times it by 5, and I'm going to get 15. And I've rewritten this particular fraction as 15 out of 35, an equivalent fraction. I'm done with that one. So I'm going to deal with the other one. I'm now going to start with 2 over 5. I'm going to rewrite that one into an equivalent fraction out of 35. So I'm going to look at the 5 and I'm going to ask what have I times 5 by to get to 35? Well, I've times it by 7. And if I've done that on the bottom, I'm going to have to do exactly the same on the top. I'm going to have to do 2 times 7 on the top to get 14. And I've rewritten 2 out of 5 as 14 out of 35, an equivalent fraction that's out of 35. Why 35? Because I just needed something that was in both times tables. Because now, if I look at the two equivalent fractions I've found, 15 out of 35 and 14 out of 35, we can make a comparison between them. Which of those two is bigger? Well, 15 out of 35 is bigger than 14 out of 35. So which of the two fractions is bigger? Well, if the 15 out of 35 is bigger, the 3/7 must have been bigger, and our answer then is going to be 3 out of 7 must have been bigger. And we've proved it using equivalent fractions. We'll do one more of these, which is bigger, 7/8 or 9/10. So we're going to do exactly the same thing again. These are two different types of fractions. One is an 1/8 type and one is a 1/10 type. So we need to rewrite one or both of them as equivalent fractions. Sometimes you're only going to have to rewrite one of them. It might be that one is rewritable to be the same type as the other. In this case, though, there's no easy way to get from 8 to 10 or from 10 to 8, so we're going to need to rewrite them both. So we need to choose something to rewrite them as that's in the 8 times table and the 10 times table, because we need to make it easy to turn 8 into and to turn 10 into. There's lots of different options we can go for. The most obvious one is probably 8 times 10, which is 80. But it's worth saying that that's not the smallest option. 10, 20, 30, 40, 5 8s are 40, 4 10s are 40. You could use 40. And actually, you would get the same answer. You would just get it in a slightly different way. But any number that's in both times tables will work. We're going to rewrite the two fractions then, one at a time. So I'm going to cover up the one I'm not looking at. I'm just looking at the 7/8 first of all. And I'm going to say, how have I got from 8 to 80? And to get from 8 to 80, I've times by 10. Now, if I've done that on the bottom of the fraction, I also have to do exactly the same to the top, because we're all about keeping these as equivalent fractions. This doesn't work if we're not using equivalent fractions. So on the top, 7 times 10 is 70. And that's that first one done. I can now look at the other fraction, 9 over 10, and we are trying to rewrite that so it's out of 80. So we're going to, on the bottom, do 10 times 8 to get 80. So on the top, we're going to have to do 9. We're going to have to times that by 8 to keep it equivalent. And 9 8s, 72. And we've got 72 out of 80. We can now look at the two fractions together. We've got 70 out of 80 and 72 out of 80. Well, clearly 72 out of 80 is ever so slightly bigger than 70 out of 80. And if this is the bigger one, then we have to go back to the original one, because the question just say which is bigger, 7/8 or 9/10. So our answer has to be one of those two. The 72 out of 80 came from the 9/10, which means 9/10 has to be our answer. And although they are quite similar, 9/10 is slightly bigger. Generally speaking, with these questions, they will be quite similar in size. It's just that one is going to be slightly bigger. A final thought with these questions. You might be tempted to say, well, surely I could just draw pictures for them. Well, technically, yes, you could, but your pictures would have to be perfect. Your pictures would have to be so carefully drawn and so carefully measured and worked out properly that you could prove definitely that one was bigger than the other, especially because these two are quite close in size. In fact, there will often be an extra line in the question that will say which is bigger, 7/8 or 9/10. You must give reasons for your answer. In fact, you must give reasons for your answer is just a fairly blanket statement, fairly generic really, that says do some actual maths. Do this maths, or something very like this maths, to prove that one is bigger than the other. As in, don't draw it. But what you don't need to do is you don't need to write anything down, you don't need to give any sentences at all. The maths is the reasons, but you must give reasons for your answers means you have to actually do some maths.